Can mushrooms build the cities of tomorrow? As we venture deeper into the potential of fungi-based construction, the spotlight turns to mycelium, the intricate root network of fungi. Emerging as a sustainable building material, mycelium is transforming various industries, from packaging to architecture. This living organism converts waste into a primary feedstock, delivering a biodegradable alternative that challenges traditional, environmentally taxing materials. In the 1990s, pioneers like Shigeru Yamanaka began exploring fungal biomaterials for construction. By the 2000s, the potential of mycelium composites began to gain traction, as innovators like Phil Ross and Eben Bayer experimented with structural blocks and insulation. Their work laid the groundwork for companies like Ecovative to patent mycelium composites, pushing this material toward commercial success. The secret lies in the hyphal network, the structural cell walls that compose mycelium. These networks can be tuned to produce composites with varied mechanical properties, tailored to specific needs. Today, advances in genetic modification and digital design integration allow for increasingly sophisticated applications, from architecture to biomedical scaffolding. But what happens when we fully embrace these living materials, allowing them to grow and evolve alongside our technological advancements? As we explore the implications, a new chapter in sustainable building unfolds. In the 1990s, the groundwork for mycelium's role in construction was laid by innovators like Shigeru Yamanaka and Phil Ross, who were captivated by the potential of mycelium as a building material. Yamanaka's early research focused on integrating mycelium into paper and building materials, while Ross, an artist, was inspired to cultivate mushrooms into structural blocks, a concept he termed mycotecture. By the early 2000s, the exploration of mycelium's capabilities attracted engineering minds like Eben Bayer and Gavin McIntyre at Rensselaer Polytechnic Institute, who pioneered mycelium insulation. Their work was pivotal in demonstrating mycelium's practical applications, culminating in a major milestone in 2007 when Ecovative filed a key patent for growing mycelium composites as insulation boards, GreenSolate. This patent marked a significant shift, propelling mycelium from experimental curiosity to a viable commercial product. The subsequent years saw companies like MycoWorks further exploring mycelium's potential in building materials and beyond, while European researchers like Maurizio Montalti tapped into local waste streams to fuel this biological revolution. With sustainable packaging, furniture panels, and even art installations emerging from these efforts, mycelium's adaptability became increasingly apparent. As we delve deeper into the commercialization and expansion of mycelium materials, we uncover the technological innovations that promise to redefine our built environment. In the race for patents, Ecovative and MycoWorks have emerged as pioneers, leading the charge in the development of mycelium composites across diverse industries. Ecovative's landmark 2007 patent for growing mycelium composites as insulation boards, GreenSolate, set the stage for their rise, showcasing mycelium's potential as an eco-friendly alternative to traditional building materials. MycoWorks, Phil Ross and Sophia Wang, patented methods for fungus structures in construction, 2011, pushing the boundaries of what's possible with living materials. These companies have not only secured intellectual property, but have also driven technological advancements, enabling mycelium to transcend its humble beginnings. Today, patent applications span from architectural marvels like the Hi-Fi Tower to textiles and leather alternatives such as myco-leather. The integration of cutting-edge techniques like robotic fabrication and genetic modification further expands the horizon for mycelium composites, enhancing their properties and potential uses. The versatility of these living materials is reshaping industries, offering sustainable solutions for everything from packaging to footwear. As patent portfolios grow, so does the promise of mycelium as a cornerstone of green construction. Yet, as this innovation unfolds, it raises a pivotal question. How do we harness nature's ingenuity while ensuring the stability and longevity of these groundbreaking materials? The journey continues. As we delve deeper into mycelium's diverse applications, its role extends beyond mere eco-friendly alternatives. Mycelium-based materials, known for their ability to transform waste into high-value products, now find themselves woven into industries like packaging, furniture, and art. These innovative composites not only offer sustainability, but also open new horizons in design and creativity. In packaging, mycelium serves as a biodegradable substitute for polystyrene, embodying a shift toward environmentally responsible materials. The same principles apply to furniture, where designers use mycelium to craft lightweight yet robust panels, pushing the boundaries of what's possible with organic materials. Artists, too, are embracing this living material, creating intricate installations that challenge traditional notions of art. The versatility of mycelium arises from its unique biological structure. Its ability to grow into complex shapes and densities makes it a prime candidate for a wide range of applications, each driven by specific species and substrates. As research continues, the potential for further technological advances remains vast, encompassing everything from 3D printing to genetic modifications. Yet, as we marvel at these possibilities, new considerations emerge. What other hidden potentials could mycelium hold, and how can we unleash these opportunities while preserving the balance with nature? The exploration doesn't stop here. In the world of architectural innovation, the Hi-Fi Tower stands as a beacon of possibility, showcasing mycelium's transformative potential. This temporary installation, erected in the heart of New York City, serves not only as an architectural wonder, but as a symbol of sustainable advancement. Mycelium composites, biodegradable and capable of transforming waste into primary feedstock, were pivotal in constructing this groundbreaking structure. These materials, composed of the intricate fungal hyphae network, offer a viable alternative to traditional building materials. They achieve this by leveraging different fungal species, such as Ganoderma and Pleurotus, which exhibit unique properties like elasticity and moisture resistance. The Hi-Fi project exemplifies the use of mycelium as an engineered living material, where its growth is harnessed to create strong, lightweight, and biodegradable components. Each layer of the tower represents a step toward a future where architecture harmonizes with nature, reducing carbon footprints while maintaining structural integrity. As we look beyond Hi-Fi, we enter a pivotal moment for sustainable architecture. Could the same principles that brought forth this tower pave the way for mycelium's role in the broader construction industry? The potential is immense, but it requires not only innovation but also a deep respect for the ecosystems we aim to emulate. As we delve deeper into the world of mycelium-based materials, the spotlight turns to the fascinating mycelial network and its intricate hyphal systems. These networks are not just the lifeblood of fungi, but the very foundation influencing the mechanical properties of the composites they form. Mycelium, the vegetative part of fungi, thrives by breaking down fibrous substrates rich in lignocellulose, converting waste into a sustainable resource. This enzymatic breakdown builds a hybrid structure, weaving the fibers into the growing fungal network. The strength and flexibility of mycelium composites can be fine-tuned by selecting specific fungal species and substrates. For instance, the Trametes hirsuta species, known for its robust mycelial blanket, excels in moist environments, offering flexibility and durability. Meanwhile, Ganoderma lucidum is celebrated for its impressive elasticity across various substrates. These properties are dictated by the unique composition of the fungal cell walls, which include chitin, polysaccharides, and proteins, each contributing differently depending on the substrate's characteristics. Commonly used fungi like Ganoderma and Pleurotus are adept at utilizing diverse organic waste streams, making them ideal candidates for creating efficient, biodegradable materials. Yet, the true marvel lies in how these hyphal systems are leading us to rethink material science. But how do we harness this potential and turn it into scalable, eco-friendly solutions? Join us as we explore the growth processes and innovative fabrication techniques that could revolutionize the construction industry. In the quest to harness fungi for construction, the engineering of growth conditions plays a pivotal role. Mycelium, the vegetative part of fungi, thrives in specific environments. Carefully controlled temperatures, typically between 25 to 30 degrees Celsius, and humidity levels around 70 to 80% are crucial. These conditions allow the mycelium to progress through its growth phases, from a lag phase of acclimatization to an exponential phase of rapid biomass increase, concluding in a stationary phase where growth levels off. The selection of fungal species and substrate significantly influences this process. Species like Ganoderma lucidum and Trametes hirsuta, paired with substrates such as agricultural waste, not only optimize growth, but also tailor the mechanical properties of the resulting composites. The choice of substrate, often agricultural byproducts like straw or wood chips, not only supports the mycelium's growth, but also reinforces the ecological benefits by recycling waste. As the mycelium colonizes these substrates, the material transforms into a robust, lightweight composite, a promising alternative to conventional building materials. Yet, to ensure these mycelium-based structures remain stable and non-living, they must be dehydrated or baked post-growth. The potential for mycelium in construction seems boundless, but what lies ahead in unlocking its full architectural potential? Join us as we delve into the cutting-edge technologies that promise to elevate mycelium-based materials to new heights. As research continues to evolve, mycelium composites are proving their mechanical mastery. These materials, derived from the root-like mycelium of fungi, offer an intriguing blend of flexibility and strength that appeals to varied industries. But what precisely gives mycelium its potential to meet industrial standards? The secret lies in its biological structure. The mycelium's hyphal network, which includes generative, skeletal, and ligative components, dictates mechanical properties like elasticity and strength. For instance, Trametes hirsuta creates a thicker outer layer, providing moisture resistance, while Ganoderma lucidum is noted for its elasticity, even across different substrates. Mycelium composites are formed when mycelium interacts with a fibrous substrate, partially decomposing it into a hybrid material. This process is highly adaptable, varying with species, substrate, and environmental conditions, each influencing the mechanical attributes of the final product. Researchers are particularly focused on optimizing these variables to standardize properties for industrial applications. This includes exploring genetic modification and using diverse substrates to refine the composite's characteristics. The challenge now is refining these composites to consistently meet industrial needs. With the potential to transform waste into resource, the question remains: how far can mycelium-based materials go in redefining sustainable building practices? This inquiry propels us towards the next chapter, where we explore groundbreaking methods for scaling this innovation. As we look to the future of mycelium-based construction, ongoing innovations in mycelium technology continue to inspire hope for greener urban development. Mycelium composites are paving the way for more sustainable building practices by offering a biodegradable alternative that not only reduces waste, but converts it into a valuable resource. This transformative potential spans a range of industries, pushing boundaries from packaging and design to architecture and fashion. With mycelium, we witness the remarkable fusion of biological processes and cutting-edge technology. Robotic fabrication, 3D printing, and genetic modification are enhancing the capabilities of this fascinating material. Researchers are continually experimenting with different fungal species and substrates, fine-tuning properties such as elasticity, water absorption, and strength. For example, Trametes hirsuta's thicker mycelium layer offers flexibility in moist environments, while Ganoderma lucidum demonstrates impressive elasticity. These varying characteristics present new opportunities for customized applications, from sound and thermal insulation panels to innovative myco-leather. Yet, challenges persist. The path to widespread adoption requires overcoming hurdles in scalability and consistency. As we explore these frontiers, the question remains: how will we harness the potential of mycelium to reshape our cities and improve the environmental footprint of human habitation?